morning, everyone. I'm Coraline at Ehmke. I work at GitHub on the community and safety team, building community management and anti-harassment features into the platform. I want to talk to you today about words and how words influence the thinking that we do. And I want to start with the question, who are we as software developers? Are we architects? An architect is someone who plans, designs, and oversees the construction of buildings, but architects don't touch tools. There used to be, I've been doing development for 20 years, and there used to be a role for software architects, but those days are pretty much long gone. I don't really think we're architects. Are we scientists? Scientists engage in systematic activities to discover new knowledge, and they do this by following the scientific method of creating and validating hypotheses based on experimental data. I don't do experiments in my day job. Are we engineers? This is a very common term, software engineer. The foundational education of an engineer, a true engineer, is a bachelor's degree or a master's degree in a specific discipline, followed by 4 to 6 years of professional supervised practice, culminating in a thesis. That's what you have to do to become an engineer, and that is not the path that many of us take, so I don't really think we're engineers either. Are we artisans? Artisans are skilled craft workers that make things by hand. They make things that are decorative or functional in nature. Artisans practice a craft and may, over time, achieve the level of mastery of an artist. The software craftsmanship movement would have us believe that we're artisans, and I think this is closer to the mark than some of the other titles that I've explored so far, but it still doesn't quite feel right. Are we cowboys? The term cowboy coder is used to refer to someone who codes independently, usually working at odds to the team that they, in theory, belong to, cranking out really dirty code that just gets the job done. So sometimes we're cowboys. Or are we astronauts? We've all heard the term architecture astronaut, someone who does too much planning up front and delays the creation of the code to the point where the design no longer matches the requirements. So hopefully we're not astronauts in this room. But we might as well call ourselves firefighting space cowboys and be done with it. Also, we like cat pictures. So why does it matter what we call ourselves? Why does it matter the words that we use? We're going to take a brief detour into linguistic theory and explore the way we think to understand the constraints that govern our thinking. This is Benjamin Whorf. He's a linguist who in 1956 asked whether or not language shapes the way we think and see the world. His experiments culminated in something called the Sapir-Whorf hypothesis of linguistic relativity, which states that language and linguistic categories influence thought. Whorf did an interesting experiment with speakers of different languages. German and Spanish is the experiment I'm going to discuss a little bit. Both languages, both Spanish and German, have gendered nouns, masculine, female, or neuter. In his experiment, subjects were shown a variety of objects and asked to describe them. The key in Spanish is la clave. Clave is a feminine noun. The experimental subjects who spoke Spanish described the key as intricate and lovely. The language that they used to describe the key was about its form. In German, the word for key is der Schlüssel, which I'm probably mispronouncing, and it's a masculine noun. The German-speaking subject experiments described the composition of the key. They called it heavy, they called it jagged, they called it metal. They described the material rather than the form. The most interesting example, in my opinion, is this bridge, Le Viaduc de Millau. Built in 2004, it's the tallest bridge in the world. It spans a valley between France and Spain. One of its mass summits is almost 1,200 feet above the base of the structure, and it's ranked as one of the greatest engineering accomplishments of all time. The French word for bridge, le pont, is masculine. The French press described the bridge as gigantic, and it used other words to describe its mass and its strength. They called it a monster of concrete. The German word for bridge is feminine, die Brücke. The German newspapers described the bridge using notably different language, Words like elegant, weightless, even the poetic, it floats above the clouds. So it seems that the Sapir-Whorf hypothesis has something backing it. Speakers of languages with gendered nouns tend to use gendered descriptions of the world around them. We're going to spend a long time on analogies and analogical thinking, so I want to establish exactly what we mean by analogies. Analogies are a comparison between things on the basis of their structure and for the purpose of explanation or clarification. Typically, we write analogies in this way, and you've probably seen this on an intelligence test. A is to B, as C is to D. For example, antelope herd is to lion, as buffet is to diner. My girlfriend and I went to an animal reserve the last couple of days, so this example seems really apt. Actually, we saw a lion hunting an antelope, and the antelope sort of got wind, maybe literally, of the lion, and made this snorting call, this alarm call, and the lion was so cute, it sort of was like, oh, damn, and it sort of slunk off back to where it came from. It was really cute. Analogies take two primary forms, metaphors and similes. Metaphors are declarative, no man is an island. Whereas similes use comparison language. It is like a poke in the eye. We use analogies to map new experiences and to draw on past experiences to determine what to do in a given situation. There's a book called Surfaces and Essences. Who here has read Gödel, Escher, and Bach by Douglas Hofstadter? A few people. This is his new book. He co-authored it with a French psychologist named Emmanuel Sander. Excuse me. The book puts forward an interesting hypothesis that describes the fundamental nature of thought. The core premise is that analogy is the fuel and fire of thinking. He talks about how we have well-defined categories of things, be they situations, characteristics of people, types of food, and we draw on these categorizations to predict outcomes or to understand new circumstances. We make analogies of situations when something reminds us of something else, or for example, when we're demonstrating empathy, we say situation X reminds me of situation Y. We're constantly faced with unknown situations, and our brain's job is to make sense of this chaotic swirl of sensory input. How does it do so? It does so through analogy making, the spontaneous evocation of words, idioms, sometimes the triggers of nameless, long, unused memories. Without categorization and analogy making between categories, we would be paralyzed by any new situation, overwhelmed by sensory data, and unable to reason about the world around us. Categorization and analogies are how we make inquiries into the nature of reality itself. The book describes two kinds of categories in our minds, marked and unmarked categories. An example of a marked category is rock. The literal definition of a rock is a piece of solid mineral material. But there's an expression that we use, he is a rock. And we don't literally mean that he is composed of minerals. So there's a second category with the name rock, and that's rock 2, which takes salient characteristics of a rock and widens its application to anything that is solid. Take the word ladder. The marked definition of a ladder is a series of bars between two uprights useful for climbing up or down something. I came across a South African proverb that I thought was really interesting. A fool is a wise man's ladder. We obviously don't mean literally that a wise man climbs a ladder made of fools. Rather, we're talking about the unmarked definition of ladder, ascending stages by which someone may advance or progress. Consider a father who tells his daughter before she goes to school, watch out for cars when you cross the street. The marked definition of car is a four-wheeled vehicle used to transport people on a road. So when you say car, you might think of something like this, with the steering wheel on the wrong side because we're in South Africa. We rented a car to get to the wildlife reserve, and I noticed every cab that we took here was a manual transmission. I haven't driven a manual transmission since I was 17, and it's kind of intimidating. So I went to the rental car agency asking for an automatic, and the only vehicle they had was an 8-seat van. It was immense. So not only was I driving on what I feel is the wrong side of the road, I was driving this really huge vehicle, and I had no idea where the left side of the vehicle was. Luckily, I didn't sideswipe anybody, but it was an adventure. Oh, and we drove for an hour down a dirt road, and an hour back through the dirt road. And when we got back to the car rental place, they were so angry because the car was like coated in dust. It was great. Anyway, the unmarked definition of a car is any vehicle that travels along the road. So it'd be ridiculous if the man's daughter would look out for four-wheeled vehicles that transport people and not for a vehicle like this. So obviously, when we tell someone, watch out for cars, we're referring to the unmarked category. Marked and unmarked categories form analogical vocabularies. As programmers, we deal with categories of things all day. Take, for example, string. Strings are common in most programming languages, except for C. And we all know what someone means when they say a string. But how did this come to mean this? Let's take a look at the literature. It's an interesting story. In 1958, in a paper called A Programming Language for Mechanical Translation, we see each continuous string of letters between punctuation marks or spaces is looked up in the dictionary. This is the earliest definition or the earliest use of the word string to refer to text that I could find. But it's not really evidence for the use of string in its modern sense. Looking at the paper in detail, we see that the data structure is not a string, but it's actually a line on a card. So string is a metaphor indicating that the letters in question are connected and form a continuous line, rather like a birthday banner. Moving to another paper from the same era, we see syntactic and semantic arguments to ALGOL. The purpose of this paper is to propose a set of syntactic and semantic augments to ALGOL designed to facilitate the description of string manipulation in that language. Note that string is in quotes here, an obvious sign that the author is performing an analogical mapping between an existing known concept, things strung together, and a new concept, a series of symbols taken as a group. Finally, we have this example, which I'm not going to read, an arbitrary sequence of constituents to stand for a string, and the use of the $sign. This is more akin to the way we use string today. String stands alone as a concept, and as a bonus, it has a recognizable symbol for identifying it. The creation of the string metaphor opened the door to similar metaphors, for example, ropes. A rope is a binary tree, and the nodes of a rope contain a sequence of characters and a weight. Ropes are used by text editing programs to allow for random access to strings of text or multiple pieces of text, so that operations such as deletion and insertion can be done efficiently. So we might say that string is to characters as rope is to strings. Every concept for a type of thing in a programming language is a metaphor that someone created by mapping an existing category onto an unmarked category, preserving its salient characteristics. The categories that we use, though, can also constrain our thinking. This is Lyra Boroditsky. She's a professor of cognitive science at the University of California in San Diego. She studies the interaction between language, perception, and cognition, and her experiments led her to believe that the private mental lives of speakers of different languages vary greatly. An interesting note about the Russian language, Russian has more words for color variations than English does. This particular shade of blue is referred to as голубой, and this one is синий. In Boroditsky's experiments, subjects were shown cards with a colored block on them, and they had in their possession other cards with colored blocks on them, and they were asked to match the color on their card, which color on their card most closely matched the color of the card that she held up. Russian speakers were much more efficient and significantly faster at identifying colors than their English-speaking counterparts. Their richer vocabulary for color variation enabled them to categorize the colors more quickly, because the categories embedded in their language made them more efficient. So what happens when we don't have words for things? How many of you have been in a situation, maybe at a holiday party, where there are lots of desserts on the table, and when you finally look up after having your first piece, you see that there's like one piece of pie left. And nobody wants to take that last piece of pie because no one wants to appear greedy. So we might describe the situation as that last piece of cake that everyone wants, but no one is brave enough to go ahead and say they want for fear of appearing greedy. That's a mouthful, right? We're able to describe in English using words, but the description that we create is not really a general category. We have to struggle to communicate the concept, creating a word soup that more or less characterizes the situation, but not in a way that's easily accessible or communicated about. In Spanish, there's a word for this situation, la vergüenza, which literally means the shame. And in Italian, this phrase, which I'm not going to attempt to pronounce, is the morsel of shame. Languages that have distinct words or phrases by which something can be categorized are more efficient. How many times have you lost an argument with someone, maybe at the same holiday party, and then when you leave, you think of the perfect response? There's a word for this in French. It translated literally means to have the spirit of the staircase. It means to come up with the ideal response to a remark right after one has left the party and is heading down the stairs. But English isn't the only linguistic poor language. We easily use the word pattern to describe something with regular features that are repeated in different situations. And we probably consider pattern to be one of those fundamental things that everyone should recognize. But if you want to talk about a pattern in French, you might learn to your frustration that there's no single word that covers this very clear analogical category. Depending on the details of what you mean, you have a variety of words that you have to choose from, and finding the word that applies most closely to the situation you're in can be difficult. And at the outset, this lacuna in the French lexicon can be very frustrating, and it seems to be a violation of common sense. The concept of pattern is so fundamental, how can a language not have this concept? In cases such as these, where one language has a word or a phrase that covers a set of situations that another language needs a variety of words to describe, we're dealing with linguistic richness and linguistic poverty. Linguistic poverty constrains the way that we think, and linguistic richness gives us a vocabulary of semantically rich mental shortcuts. Spoken languages are not the only languages that suffer from lacunae. This is a sampling of built-in types in Ruby. We have lots of them. Each type can be considered an analogical category, as it represents a core set of characteristics and behaviors that define a type of thing. There are only 6 built-in types in JavaScript. And if we overlay them, we see that the two languages have 2 primitives in common, object and string. There's overlap with Boolean. Ruby has true and false. JavaScript has Boolean. There's overlap with the concept of nil. There's null and undefined. In that case, JavaScript is a little bit more semantically rich. But it's clear that Ruby has more categories of things, and that makes it more efficient for us to talk about and reason about those things because we have languages for them. If you want to describe these core concepts in JavaScript, you have to create a lot of code, you have to use a lot of words, and create that word soup once again. When we have words for concepts, we can more clearly identify them, reason about them, and communicate about them. So what do we do when we don't have a word for something? We could invent a new word, but as programmers, we think naming things is hard, and creating new words is even harder. So what we do is we borrow words instead. Many of the day-to-day terms that we use in software development are actually borrowed from other situations. Rails provides us with scaffolding. Scaffolding in the construction industry is a set of metal construction that lets you erect structures really quickly and safely. Our test suites may have fixtures. All the fixtures are evil. In electronics, a fixture is actually a physical item that holds a circuit board in place to enable testing. When we deploy to production, hopefully we have a smoke test to make sure that things didn't go awry. Smoke test comes from plumbing, where a harmless smoke is pumped through pipes to detect leaks. We in Ruby like to use modules. Industrial design modularity refers to an engineering technique that consists of building large structures from smaller pieces. If there are any UI people or front-end people in the room, you probably have created wireframes. The term wireframe comes from architecture, an old practice of using physical wires to represent three-dimensional objects. And one of the interesting ones is scaling. This one took a little bit of research to figure out where that word actually came from. The device on screen is a pantograph. It's a mechanical linkage that allows the movement of one pin to control the movement of a second pin. And depending on how you configure the pantograph, you can make, by tracing over an image, you can make it larger or smaller. And that process is referred to as scaling. So using the same principle, different kinds of pantographs are also used for other sorts of things, including sculpture and minting and engraving. The words we use to categorize problems reduce the number of data points that we have to parse. Problem solving is about identifying patterns. Take this for example. This is easily recognizable as a graph. Now it doesn't have a key, so we don't really understand what we're seeing in the graph itself, and it's very irregular, so it'd be very difficult to identify a pattern. But if we zoom out, we lose some of that detailed information, but we get a bit bigger picture that gives us a different perspective. At some point, some people will recognize this as an audio waveform. We see patterns in it, but we generally don't have a language to describe those patterns. If we zoom in just a little bit, the pattern becomes more apparent. There are spikes, regularly spaced spikes. And we might guess that these represent peaks in volume, but we really don't have language to describe what's happening. But an audio engineer has a vocabulary for this pattern. She would know that the peaks correspond to beats and be able to correctly guess that the spikes represent drum hits. An audio engineer would be able to see the song in this graph. The utility of data comes from our ability to perceive patterns in it. We can hold more active patterns in our memory if we have words for them. That's why we do use names for things and why names are so important. They're cognitive shortcuts. The identification of core analogical patterns in programming is so important that we've actually invented a vocabulary purely for describing patterns. And when I talk about patterns in the context of a software conference, you would be forgiven for thinking of the Gang of Four: Eric Gamma, Ralph Johnson, Richard Helm, and John Vasides. Their design pattern book was published in 1994 and has been reprinted more than 20 times, and they've sold about 500,000 copies. The book introduced 23 core patterns. Each pattern is an analogical mapping between an unmarked category, such as visitor, and an observation about a solution. Giving names to the patterns lets us identify them and discuss them without confusion, and implement them in an efficient manner without creating a bunch of word soup. But the concept of a pattern language was not invented by the Gang of Four. This is Christopher Alexander, a noted architect. He's been involved in over 200 projects worldwide. He reasoned that the users of a building have a better idea of what they need from a space than an architect or a designer ever could. So he produced and validated a pattern language designed to empower anyone to design effective buildings. His book, A Pattern Language, very creative title, contains 253 patterns, about 10 times as more as the Gang of Four book. Each pattern describes a problem and its corresponding solution. The patterns identify pairs of relationships between problems and solutions, and each pattern was reviewed by other architects for practicality and beauty. The very existence of the language that we use to describe common patterns actually comes from an analogical mapping between the field of architecture and the field of software development. But even Alexander wasn't the first person to come up with the concept of a pattern language. This is Gottfried von Leibniz. He was a natural philosopher, aka alchemist, who strove to create an alphabet of human thought, a universal way to represent and analyze ideas and relationships between ideas by breaking them down into their component pieces. He did this by means of a thought alphabet. And the core hypothesis of the thought alphabet is that all complex ideas are made up of simple ideas, each of which can be represented by a single character. And his work in this area was critical to the development of the binary number system and his most well-known invention, calculus. So we use pattern recognition to identify common problems and pattern languages to describe their solutions. The complex systems that we build emerge from combinations of these problem-solution pairs, and these systems are built into metaphors embedded in our pattern languages. Does that mean that pattern languages represent a lingua franca and remove the need for individuals to form their own mappings? Not really. We draw on past experiences to categorize new experiences and put them in context. So the more diverse a group of people is, the larger the range of experiences that we have to draw on for our metaphors. And there have been studies that prove that diversity in a group actually improves problem-solving capabilities. People from different backgrounds have different experiences, different ways of looking at the world. People who speak other languages might have shortcuts, cognitive shortcuts, to describe concepts that we don't have in English. People who transitioned into tech from other fields have a great deal of experience with the world that we as software engineers maybe were insulated from, so they have key insights to deliver as well. There was a really interesting study by Catherine Phillips, Katie Linguistic, and Margaret Niels from 3 different universities. They conducted an experiment with college fraternity and sorority members. The subjects were divided into groups of 4 or 5 and presented with a murder mystery scenario. About 15 minutes into their discussion of a solution to the murder mystery, another person was injected into the experiment. In the control group, another member of a sorority or fraternity was injected into the group, and for the experimental group, a person outside of the Greek system was introduced into the group. The homogeneous groups, the ones consisting solely of fraternity or sorority members, felt more confident in the solution that they came up to the murder mystery. But actually the groups with outsiders were more accurate than the control groups, even if the newcomers didn't bring new ideas to the table. Their presence created a sort of social awkwardness that actually influenced the group's problem-solving abilities. Regardless of whether we draw on a common language or individual perceptions for the categorization of experiences, the conceptual categories that we work on can be slippery, and this leads to ambiguity. But is ambiguity always bad? When I'm not working for GitHub, I'm working on an AI project called Sophia. And the goal of Sophia is to be able to understand and actually create metaphors. I spend a lot of time on my data model. I'm using Neo4j, a graphing database. And I have this concept of contexts, and contexts have expressions. So an example of a context is disposition. And disposition might be expressed as cold or warm or mean or unkind, and other words like that. I have another context called temperature. So temperature might be described as frigid or tropical or arctic or chilly and words like that. And the graph database shows that both temperature and disposition share 2 expressions, cool and warm, or cold and warm. So this leads to ambiguity when I'm parsing a sentence like, that cat is warm. So when Sophia comes across a sentence like this, she doesn't know if we're referring to the cat's disposition or the cat's temperature. So what she does is she scans ahead. That cat is warm. She's been sitting in the hot sun all day. She sees the word hot and the word warm and correctly infers that we're talking about temperature. I had a high school English teacher who wrote on a paper. She was really annoying. She always gave me an A-. And at the end of the school year, I was like, how come I never got an A on any of the papers I submitted to you? And she said, if I gave you an A, you'd stop trying. And I was like, I was so angry. On one of my papers, she wrote, there is no artistry in ambiguity. And I disagreed so strongly, because art is about ambiguity. We can use the slipperiness of analogies to form new analogies. The University of Bamberg's research team, led by Dr. Claudia Musch, makes the argument in a paper that was published last year. In a small study, participants were shown paintings, and researchers found that the higher the degree of ambiguity within an artwork, the more participants liked it. Insight from looking at an artwork can be triggered by its ambiguity. The pleasure that the subjects experienced by looking at these paintings was not related to the process of figuring out exactly what the painting was about. In the study, the subjects rated each painting on their interest and how strongly it affected them. And then they saw the paintings for a second time and were asked to rate the painting's ambiguity. The most striking result from this survey is the higher a subject rated the ambiguity of a piece, the more they enjoyed it. So a little ambiguity can go a long way, and embracing ambiguity can lead to the creation of new analogies. The creation of an analogy means that we're leaving out details and focusing on a larger picture. The converse of this situation is when we focus too much on details. And when we focus too much on details, we're actually unable to solve a wide range of problems. And there's a name for this. It's called functional fixedness. It's a cognitive bias that limits a person to using the object only in the way it was designed to be used. This man, Carl Duncker, invented the term functional fixedness for describing the difficulties in visual perception and problem solving that emerges from the fact that one element of a problem has a fixed use, which actually has to be changed in order to solve the problem. His most famous experiment is the candle problem. The situation is defined by three objects: a box of tacks, a candle, and a book of matches. The task of this puzzle is to affix the candle to a wall. When given to undergraduate students at Stanford, only 23% of respondents were able to correctly solve the problem. As I mentioned, I work for GitHub. GitHub's full of stickers. There are stickers up here for after my talk. But if you know the solution to this problem, if you can figure out how to put the candle on the wall using only those items, the first 5 people who come up to me with the correct answer will get a GitHub gift card. Another example of functional fixedness is the tragedy of the Titanic. As we all know, the Titanic struck an iceberg. People were thrown into the water. There weren't enough lifeboats. The people in the water suffered from functional fixedness. They saw lifeboats as a rescue mechanism and an iceberg as an obstacle that sank the ship. No one swam to the iceberg to climb up on the iceberg and wait for rescue. There are ways to overcome functional fixedness. One of the strategies is called the generic part strategy. You break something down into its components, you describe the component. If your description implies a use, you repeat the process. Overcoming functional fixedness saved the lives of astronauts on Apollo 13 from certain deaths. There were lots of catastrophes that happened on this particular space mission, including the fact that the lander module, where they were hiding out because the capsule was no longer habitable, had CO2 scrubbers with a square filter, whereas the capsule had round filters because they were designed by 2 different companies. So the engineers on the ground had all of the items in their possession that the astronauts had in their possession and had to figure out how to jerry-rig a solution to the problem. And one of the things they did was the binder, the mission book that the astronauts had on hand, they told the astronauts to tear the cover off and use that as a raw material to solve the problem. So they were able to overcome functional fixedness by looking at this book not as a book, but as a source of raw materials. When we first approach a new idea or a situation, the impressions that we form are shallow. Novices notice surface features because they only understand, if you think about it, the marked category of a given word or concept. They lack the complete understanding that comes with mastery. For an expert in the domain, deep features are obvious. They're not elusive, they're the most salient features. Expertise involves creating, analyzing, and expanding an analogical category vocabulary. There was a study conducted in 1997 of people who worked in a molecular biology lab. And the researcher looked at the language that the scientists use to describe solutions to problems. And they found that analogy making was a critical and repeated component of the best solutions that were put forward. And that these analogies reflected structural similarities rather than surface level features. So the accumulation of new and novel analogical categories is the mechanism by which expertise in a given field is achieved. And over time, each human discipline acquires more of these metaphors and more of these analogical categories and is able to map between these categories with greater ease. This doesn't mean that a scientist in 2017 is smarter than a scientist from 1717. The analogical leaps that were required at the beginning of a field of discipline are just as significant as the analogical mappings that happen later. We just make it easier as we go on, and this process is similar to a rock climber leaving batons for the people who come after to have an easier ascent. I mentioned a couple of times that analogy making helps us deal with novel situations. And there are lots of examples of like architects and painters and scientists who, thanks to a fresh analogy, were able to transport a concept from one domain into a different domain. And this is a cognitive activity that some people have a gift for. And it happens when we explore unlikely connections between concepts and reveal relationships that are not obvious. We often come up with a label for a complex situation by using an example from our everyday lives, from a concrete situation that's analogically linked, and then borrowing the name of the standard situation. And this strategy allows us to create verbal labels for new categories of things. Almost every talk that I give picks on Edsger Dijkstra. He's beloved in the computer science community, but I have issues with a lot of the things that he says. And I want to read you a quote. "It is the most common way of trying to cope with novelty. By means of metaphors and analogies, we try to link the new to the old, the novel to the familiar. Coping with radical novelty, however, requires an orthogonal method. One has to approach the radical novelty with a blank mind, consciously refusing to try to link it with what is already familiar, because the familiar is hopelessly inadequate. Coming to grips with a radical novelty amounts to creating and learning a new foreign tongue that cannot be translated." I disagree, and so does Douglas Hofstadter. Hofstadter counters this by saying that thanks to categorization through analogy making, we have the ability to spot similarities and exploit the similarities to deal with the new and the strange. And perhaps Nietzsche said it best when he described truth as a mobile army of metaphors. So we've talked a lot about categories in a linguistic sense, but I would be remiss if we didn't talk a little bit about category theory. Category theory is essentially the study of structure. It's a study of things and the mappings between things, the translation of objects from one thing into another kind of thing. And its main draw is its ability to connect disparate fields. It's a skeleton to hang knowledge on. Jocelyn Ireson Payne put it this way: category theory is a great source of unifying concepts and organizing principles. It reflects the power of abstraction. By throwing away details, an object's structure reveals itself. The two main sort of principles of category theory, the two main objects, the two main concepts are objects and morphisms. Objects can be thought of as sets, and arrows represent functions. So for the set ABC, the function F1 produces D, E, and F. Categories are simply collections of objects, and translating this into programming, we might have application user as a type of object. Every object in category theory has something called an identity function, and when called, it returns the definition of the object. This is similar to the marked category of a kind of object, and in Ruby, we might use self to refer to the thing itself. So when we have a user object called user, if we execute the name of the variable, we get the variable back, and that's an identity method. Morphisms in category theory tie two objects together, a source object and a target object. So we might have an application user that we call, or a set of application users, and we call to string on them, and we get DEF, which are string representations. When we call a function on an object in Ruby, we essentially perform a morphism. We run into problems when functions have divergent return types. And this is a problem that we face quite often. We have to do nil checks all the time, because if a user has a name attribute, sometimes when we call name, it returns nil, and sometimes it returns string. In a dynamic language, we can even attempt to invoke a function that's not defined and not find out about that until runtime. And this is akin to trying to perform a morphism that doesn't have a corresponding function. It leads to an exception being raised, which is a break in control flow. And problems arise for us in dealing with exceptions, and they violate the fundamental principles of category theory. We can get around this by using method missing, which replaces an unknown function with a known function. But method missing allows us to maintain control flow, which is good, but it comes at a higher cognitive overload. There's a performance impact, and it's difficult to reason about. So when we expect a return type and we don't get it, bad things can happen. Inconsistent return types, where a function returns either string or nil, leads to exceptions. So the newest version of Ruby has the lonely operator, which I think is a wonderful name for this sort of thing. And it does something really interesting. It replaces a method that would ordinarily raise an exception with what in category theory we would call an ID method. So it swaps out an unknown method for a known method. There's a great video series on category theory on YouTube by a guy named Bartosz Milewski. I'm guessing that's how he pronounces it. One of the points he makes is that traditionally we have attempted to solve problems by breaking them down into components and composing an overall solution. And scientists have been following this practice for centuries. They've been searching for these sort of Platonic ideals that describe the makeup of problems they're trying to solve, or even the makeup of the universe itself. And that's also the philosophy of Unix and the philosophy of scripting languages, breaking problems down into small pieces so that we can solve them. But there are places where this approach to problem solving really breaks down. Object-oriented programming brought in abstractions that let us reason about larger pieces of problems. And functional programming brings us even closer to the ideal of applying category theory to our software. It seems that the evolution of computing is moving away from small component and composed solutions and toward abstractions. With the emergence of string theory and set theory and category theory, we're starting to realize that it's through abstraction that we can derive the most meaning from the world. Abstraction is the key to understanding reality. When we program, the very creation of a class is a form of categorization, and defining methods is simply defining morphisms on the categories. So categories are at the core of object-oriented programming. Now, how does this tie back to analogies? Early scientists were able to understand that water moved in waves. So the marked category of wave, which is literally the movement of water, they were able to come up with a function called frequency, which returns the period of a wave. Abstracting the notion of a wave into wave 2, moving from the concrete example of a wave to a more abstract, unmarked category, led to an important innovation. The breakthrough occurred in 240 BC when the Greek philosopher Chrysippus speculated that sound was a kind of wave. 200 years later, his ideas were more fully developed by the Roman architect Vitruvius, who explicitly likened the spreading of sound waves from a source to the circular ripples in water. So by asking, what if X is a wave, we can perform analogical mappings to gain insights and knowledge. For example, if we consider mood a wave, if someone is bipolar like me, they have peaks and valleys in their mood. And if we graph them and express them as waves, we might see that the period of depression is predictable, and that allows us to handle the situations a little bit better. So asking what if X is a Y2 is the foundation of analogical category mapping, and it's the foundation of a lot of innovations across the breadth of human enterprise. And categorization means ignoring extra details. It doesn't matter that sound is not a physical substance that waves move through. It doesn't matter that mood doesn't have actual motion involved in it. Things that were different, when we apply them to unmarked categories, suddenly become identical. So sound and water become identical. Samantha and Roger become identical because they're both users. It's about epistemology versus ontology. It's about how we reason about things versus how things actually are. So we come back to the question of who are we really? We're curious people. We're natural philosophers. We're machines that turn varied sensory input into metaphors and analogies. We recognize ideas and ideals, their taxonomy, and the interrelatedness between them. We create systems for categorizing every conceivable thing in the known universe. And in the end, when we gain an understanding of these complex systems and models that we create, we expose and exploit connections to uncover and manipulate knowledge. This is a picture of my personal copy of a book called The Divine Pymander. It's an alchemical text that was first translated from Latin to English in 1650. It consists of 17 tracts, exploring concepts such as creativity, order, manifestation, the nature of God, and interestingly, monads, but not monads from functional programming. The monad referred to the primacy of essences. The book ends with this sentence: "The image shall become thy guide, because sight hath this peculiar charm. It holdeth fast and draweth unto it those who succeed in opening their eyes." In modern language, and maybe more in keeping with the subject of his talk, we might translate it as metaphors will guide us. Ideas persist and draw us closer, bidding us to recognize them. Software development is essentially an inquiry into the nature of reality. It's a reflection of a worldview made concrete in code. We study ideal objects and bring them into existence as networks of interrelated instances, and we manipulate their interactions and connections to change the fundamental nature of the modern world. But as software developers, we tend to draw our metaphors from hard science, from architecture, from engineering, from mathematics. Why should we limit our problem-solving vocabularies and our metaphors to these disciplines that we seem to worship, when the corridors of human thought are so rich and so vast? So let's cast our nets wide. Let's step outside of the bounds of the constraints of our thinking. Let's read everything, broaden our interests, look for metaphors and conceptual categories that we can apply to our science. Let's use our powers of categorization and analogy making to create breakthroughs, to advance ourselves and advance our field in new and unexpected directions. Let's be geniuses. Let's be innovators. Let's be creators. It's what our minds were designed to do, and it's what we were born to do. Thank you.